Alright, so let's look at the correlation coefficient, and the research questions that we have are: what is the relationship between your variable first one and your variable second one? And you have these listed within Blackboard, and so I'm going to use test 14 and test 15 for example purposes. And so let's look at our syntax, and we have the frequencies command where I'm asking for a bar chart and a pie chart and just the mode in the statistics, because female or gender is a nominal variable. Then for cohort in the class data, it's an ordinal measure. So again, I asked for the bar chart and the pie chart, and I've got the min, max, median, and mode. Then for the variables that are intervally scaled, like age and the two tests, I'm going to go ahead and ask for everything there because they're intervally scaled. So I can have a PP plot because I need to check for normality. I've got a histogram, so I can overlay a normal distribution on that. And so this first part, all of this is just checking our assumptions and checking the data to make sure it's okay and getting some descriptive information. This part right here is the new part. Whenever we're running a Pearson R or a point by serial or a phi, you can run it with the correlations. Notice that I don't have cohort in here. I have female because it's dichotomous. I have age because it's interval, and so then female relationship with age and with test 14 and test 15 are going to be a point by serial relationship because that's a dichotomous variable with intervally scaled variables. The relationships between the intervally scaled variables, in other words age, test 14 and test 15, are all going to be Pearson R's because it's two intervally scaled variables. Unless the normality of these tells us differently, that we can't, if we find out we can't assume normality, then we'll have to run it as a non-parametric. So actually I removed female from the non-parametric because it makes no sense to have gender, which is a nominally scaled variable, in an analysis that will have that is based on rank, because there is no inherent order in females, or gender is the variable. So I'm looking at cohort, which is ordinal, age, test 14, and test 15, which is interval. Now remember, you can run intervally scaled variables as a non-para in one of two situations. If you don't care about their shape, you're only interested if they have a if they're ordered in the same way, or if you fail to meet the normality assumption and instead you move to a non-parametric analysis. So the cohort variable must be run as a non-parametric because it's ordinally scaled. So ordinal variables obviously have no shape, and so they cannot be run as correlations. They have to be run as non-parametric correlations. Age, test 14 and 15 do have order, do have shape, but if we're only interested in the order, we can run them as non-para. And so that's what's listed here. Here's how you would get this syntax. Of course, you know how to get this top part, but here's how you get this bottom part. You go to Analyze, Correlate, and then Bivariate. And then you get a bivariate pop-up box that comes up, and you would put all your variables that you need to test into the variables box. You just simply move them over. And you have the Pearson R. If you want the Pearson R, then you check that box. Remember, you would also check this if you have dichotomous variables. And so two dichotomous variables would be a phi. If you have a dichotomous and a intervally scaled variable, for example, female in age, then that's not a phi, it's a point by serial. It's not a Pearson R. Remember, the phi and the point by serial are mathematically equivalent to the formula for the Pearson R. That's why you can use those for those purposes. The Spearman, again for ordinal data, would be you would use for the cohort with age, or cohort with test 14 or 15. You would not use the Spearman for the female, which is nominal. This is going to give you asterisks next to the statistically significant correlations. So you can uncheck that if you don't want to see them, or you can check it if you want to see them. So then you run that, and what you have is you'll get a frequency box for the cohorts, which we have here, and you'll notice that the first one that shows up is cohort 3, which is the most recent. In other words, they're in year 1, and so that's cohort 3. Cohort 2 is in year 2 in this model, or in this data set, and then cohort 1, which is the oldest cohort, is in their 3rd year. And then same kind of breakdown in the frequency for the gender, with 1 being the women and 0 being the men. And then we have our descriptives for our intervally scaled data, and we see the mean for the age is 39, standard deviation of about 9 years, and you can see the 95% confidence interval there for the mean. And here's the skewness divided by the standard error of the skewness, and the kurtosis divided by the standard error of the kurtosis. Now you'll notice that this exceeds what we would allow as normal, even in the more liberal sense. So let's check the other ones. We've got test 14. Here is, we're still okay there. Here is test 15, so we're still okay there. If we look at our normality test, in the KS, all of them come out to be statistically significant, but in the Shapiro-Wilks, only the first one, age, is statistically significant, which means we feel it deviates enough from normal to not consider it normal. So that's one incidence of that, and another one here with the kurtosis. So the two pieces of evidence that we have so far are telling us that age might not be normally distributed. The others seem to be okay, because again this one is very conservative, and so doesn't appear to be distinguishing among them. So when I get something like that, then I still want to look further to see if I can see anything visually inspecting the data. So I could look at the histogram and of course the QQ plot. You can see there is a curvature in this QQ plot for age, and then also if you impose a normal distribution over the frequency distribution of age, you can see it's not quite looking like a normal distribution. There's some peaks there, so there's some issues with that. In comparison, you've got the test 14, which looks pretty good, and here, although it is maybe a bit kurtotic, it does seem to follow a normal distribution fairly well, and you should be able to look at the picture and say, okay, this is a little peaked, so what does that mean in terms of the kurtosis? Well, here is our kurtosis information for test 14, and we see it's a little positive, and you would say, yeah, it's a little peaked. And so same thing over here with test 15. If we go back to the descriptives for test 15, we also see it's a little peaked. Slight negative skew slight negative skew for test 14 also. And so we should be able to see that in the figure. And you can see here that test 15 looks okay in terms of normal distribution. So what I would conclude then is I'm going to have to reject that the age is normally distributed, because I have 1, 2, 3, and really 4, 5 pieces of evidence that are telling me this is not normally distributed. So, but these others, I don't have that evidence, and so I'm going to consider them normal enough. And just to remind you how you get these histograms. Now the histogram and the Q plot, you can get them through here within the examine, the explore command, NPP plot and histogram. But you can also get them another way that might be useful to you as you're making charts. You go to graphs. Instead of, we usually start with analyze, but in this case you're going to graph, chart builder, and then the chart builder box will pop up. And if you move age into this box here, you just drag it, then it will build a histogram for you. You can also, because we need scatter matrices, instead of selecting histogram, you would select the scatter dot box and select this one right here. And so instead of a bar graph here, you'll get a scatter matrix, and you will move the variables there one at a time that you want to be in the scatter matrix. In my case here, I included age, test 15, and test 14. And so you can, what you're looking for here, remember one of the assumptions of the correlation is that they have a linear relationship. And so here between test 14 and test 15, you can see a very nice lineup of the circles into a line. So you definitely feel comfortable that there's a linear relationship with test 14 and test 15. With age in test 14 and test 15, you don't really see a linear relationship necessarily, but you also don't see any kind of other pattern, some kind of curvature or something that would make you think that that maybe there's something strange going on. There's simply it's just a cluster. So so then I feel comfortable in proceeding with the test. But remember, because age was not normally distributed, I'm not going to consider age when I am looking at my Pearson R. So what I would do actually, if I was looking at this, is I would completely black out this column, because not if I was presenting this in APA, obviously I would actually take it out, but in the case of just for our purposes now, because I'm not going to consider age as normally distributed, I'm going to work with just test 14 and test 15 as Pearson R, and gender with 15 and 14 as point by serial. So then you'll see the ones on the diagonal, you'll see the relationships or the Pearson R or point by serial on the off diagonals. You'll also see that it's symmetric. Let me take this off so you can actually see. So you'll see, negative 8.52, but we're not working with that one. Negative 0.097 between female and test 14. Notice it's not statistically significant. There's no asterisks there. And you see the exact same thing over here, which is female by test 14. And here we have test 14 female. So it's a symmetric table. You can either report the bottom triangle or the top triangle, If you were not going to, if you were going to make a APA table, you would only include the ones that you are reporting a Pearson R, point by serial, or fee by, but we don't have any fee in this case. So you would make a matrix with 3 variables. Female would move to this slot, or you just have 3 rows. Female, test 14, test 15, and then 3 columns, female, test 14, test 15, and either bottom or top you would have your relationships. Now you might wonder, if you're looking at this, how I was able to get the ones on the diagonal, and then that's separated out from the p-values, and then that's separated out from the n. Well, SPSS won't by default do this, but what you can do very simply is, when you have your correlation matrix there, and this one happens to be the Spearman row, but it doesn't matter which one, if you click on it and then right click, or if you double click on it, you'll get this selection, and you have these things called pivoting trays in SPSS. Well, the pivoting trays allow you to move around. So when I first had this box pop open, you've got the type, the variables, the statistics, and then variable 2 in the column, and you can see that that the statistics are in the rows, variable 1 in the rows, and then variable 2, and it's also got the types. So all I did was I grabbed the statistics, which was here, and I click on it and drag it above the variables, and that allows the table to turn from this table, where you have the p-values and n's directly under each of the ones, instead of what you want, which is a nice clean table where you have the relationships listed there and the p-values and the n's are somewhere else. So because that's the way you're going to have to set it up for when you're doing your APA table. Now notice that none of the relationships with cohort, either with age, test 14 or test 15, are statistically significant. None of the relationships between age and test 14 or 15 or with cohort are statistically significant. What is statistically significant is the relationship between test 14 and test 15. However, remember this is a Spearman's row, and test 14 and 15 are intervally scaled. So this is looking at their relationship, ignoring their shape. If we go to the Pearson R over here, we get a slightly stronger relationship of 0.962 between test 15 and test 14, and they did not violate the assumptions, so I would go with the Pearson R for test 14 and 15 because the assumptions were met. I looked at the linearity, and they are demonstrating a linear relationship, and there's no reason to not look at the Pearson R, so you would report that. In the case of age, because it did violate the assumptions, I would report the Spearman's row. In the case of cohort, I would report the Spearman's row because it's an ordinal variable. So that's how you decide. It's very important that you know the scale of the variable and what it is that you're trying to say. So let's just work with the one with what is the relationship between test 14 and test 15. So as can be observed in the correlation matrix, there was a statistically significant relationship between test 14 and test 15. The relationship was positive and nearly perfect. And so you have a 0.96, which remember is the Pearson R for test 14 and test 15. And if you square this, remember you have to square it before you can compare. 0.96 squared is 92.16, or 0.9216, and we can express that as a percent, and that is the effect size, which again we'll talk about some more later, but that's the magnitude, the size of the effect of test 14 and 15, or the amount of shared variance between test 14 and test 15. The p-value given here, as we're used to, with a space before and after either the equal sign, or here we have a less than sign. And we're reporting it as this because in our table you can see that it's statistically significant at the 0.01 level. That means it's less than 0.01. And so if you actually double clicked on this number in SPSS, you would find out how many digits after the decimal you have an actual number besides 0. Remember, never ever ever give a p-value or report out a p-value of 0, because a p-value of 0 in essence means that the results that you obtained are impossible. So how could you have obtained them if they're impossible? So you will go through and find what the relationship is between the test variables that you were given, and you will briefly state what the result is in your write-up.